Morning, everyone. I hope you're good. My name is Rocio Garcia, and I work at Sustainable Innovations. I am also the communications manager for the ALIGNED project, and I'm very happy to welcome you to this online workshop, this online training about LCA for bio-based products. We have a very important morning today, and before I present you the speakers and my colleague Michele Poncelli, first, I would like to give you some guidelines for the questions and answers. So at the end of the presentations, of course, you will be able to make questions, but we're a lot today. We're more than 150 persons, so it will be tricky for us to filter all these questions. So just on the Zoom, you have this option to write on the bottom of the Q&A, but you can also write your questions on the chat. So please do it this way. Also, you can send us an email to info@alignedproject.eu if you need to leave the workshop. And for the persons that need to leave earlier, this workshop will be recorded and we will upload it, to our YouTube channel next week. We will send you the link and everything. So thank you again for being here. And yeah, Michele Poncelli from LIGNICOAT can explain you the agenda for today.
Yes, thank you very much, Rocio. I am Michele Ponzelli from ALIGNED Innovation. We are partner of LIGNICOAT, and alongside with ALIGNED, we decided to make this webinar with this training on LCA for bio-based product. I would like to thank you. We didn't expect so much people interested in this training, so we are very, very happy for that. We hope that this training session will be a valuable opportunity for all of you for expanding your knowledge on LCA and bio-based products. And we have an exciting agenda. I hope you stay with us until the end, until 12:30. So we will start with the coordinator of our two projects, so Massimo Pizzol from ALIGNED and Aitor Barrio from LIGNICOAT, which will give a very brief overview of our project, what they're all about. And then we start getting into the core of this training. So with Leo Staccioli, that is our partner of LIGNICOAT on LCA, we'll start with introducing why we do LCA and the first session on scaling up from lab to industrial scale. So each set, and then we will have calculation methods. We will have a break around 10:20, and then we will have another two sessions, calculation methods and carbon accounting. Each session will be will contain a theoretical background. There will be also a practical example, and then there will be a Q&A session. And as Rocio just said, we invite you to write it in the chat, in the Zoom chat. So without further ado, let's get started. So I'm very pleased to introduce you the coordinator of LIGNICOAT project, Aitor, and then also Massimo. So please.
Thank you, Michele. I'm going to share my screen. Can you see my screen? Yes, I think it's now available. No?
Not yet.
Sorry. Now?
Yes.
Okay. Thank you, Michele, as commented, and Rocio for the introduction, and welcome to everybody to this webinar. As commented by Michele, I'm going to explain very briefly what is the main aim of LIGNICOAT, that is based on the title is Sustainable Coatings Based on Lignin Resins and Bioadditives with Improved Fire, Corrosion, and Biological Resistance. The main topic of the project is coatings, and as most of you know, one of the big problem is the use of fossil-based coating that release volatile organic compounds and the regulation are more and more restricted in the coming days. So it is very important to reduce these volatiles. This is the scheme. The aim of the project, as commented, is to demonstrate that technically and economical feasibility of the use of this lignin as raw material to produce 3 different bioresins for different applications that could be wood, metal, furniture, automotive, flooring, machinery, and paint industry. So we are going to start with lignin, craft lignin, organosolid lignin, and also hydrolysis lignin. We are going to prepare intermediates that are lignin polyols, lignin polyacids, and epoxidized lignin by modifying this lignin. And with these intermediates, we are going to produce resins. We are focusing alkyd, epoxy, and polyurethane. And with these 3 types of resins, we are going to formulate coatings for wood and metal, taking advantage of the main properties of lignin that could be improve the fire performance, improve the anti-corrosion performance of these surfaces, and also antimicrobial and antiviral performance. Apart from that, we are going to introduce also some bioadditives like enzymes and active compounds in order to increase the antiviral and antimicrobial activity. These are 3 examples of the developments that we are currently doing. The project will finish in November, so we are very active in the formulation of these coatings, polyurethane coatings for good base on lignin polyols, mainly for fire performance, alkyd resins on metal based on lignin, mainly for corrosion application, and also we are formulating epoxy lacquer for coil coating on aluminum, improving the surface performance. The objective is to reduce, as commented, carbon emissions by 50% to fossil-based market reference using water and also using biosource, the resin and the bioadditives, and increase the bio content of lignin. Bio content range between 10 and 50. The impact beyond the coating industry is to create new cross-sector interconnection, because nowadays lignin is not used for these applications as a resin. Can be used as an additive or like powder or some additives, but not as a resin. So we are creating a new cross-section, new bio-based value chain based on lignin to coatings, new bio-based chemicals, as commented. The intermediates can be used for other applications like adhesives or others. So we can produce lignin polyols, epoxies, polyacids, and resins that can be applied to other industries. Coatings formulation with bio content bigger than 25, and new jobs opportunities. This is our team. We are 14 partners in 8 countries, 9 industrial partners, 4 research and technology organizations, and 1 no-profit organization. So we are Foresa, Tecnalia, Itacil, and Barpimo from Spain, Bencores and Ecode Arditech from France, Vito from Belgium, Westlake Epoxy from Netherlands, North from Norway, Axia from Germany, and Iris and AP from Italy. And this is the contact details for our project, the website, the email, and social media links. So this is all.
Thank you, Ettore, for the introduction. Massimo, if you want to take the floor and share your screen and talk us what ALIGNED is about.
Yeah, yes, and I hope you can see the presentation.
Yes.
Thank you. So welcome everybody. I'm Massimo Pitzel from Marburg University. And I'm going to present the ALIGNED project very briefly, and that I coordinate together with my colleagues here at the Department of Planning, Sustainability and Planning. So ALIGNED is aligning life cycle assessment methods and bio-based sectors for improved environmental performance. This is a EU-funded project. And the overall purpose is basically to make LCA methods that are available already for scientists, make them more available or more usable or more accessible to people who do LCA in practice in the real world. Via a selection of the best available methods for the modeling of specifically the case of bio-based products. In particular, we have 3 objectives in ALIGNED. The first is to improve, harmonize, and align LCA methodology, because you can do LCA many different ways. So you need a sort of set of tools that can work well together for the assessment of bio-based products. And then this sort of harmonized methodology is going to be tested in different case studies within the project. Is being tested actually as we speak. In particular, 5 different sectors are covered in the project. And then we want to involve the stakeholders in this process and also communicate and disseminate our findings and our tools. And this workshop is part of this effort, in fact. We are several partners in this project. We have 4 universities, 6 case study companies, 2 research SMEs, and a sector organization. And you can see the whole group in this picture taken last year at our project meeting. What is the structure? First, we have a work package, which is called the work package 1 shared modeling framework and learnings. That's where we put together all the relevant methods, LCA methods for the assessment of bio-based products. And my presentation today will be based on the findings from this work package, in fact. And then we have 6 case study packages where, in collaboration with industry, we test the methods on different case studies. And then we have, of course, activities of stakeholder involvement, dissemination, communication, like this one today. What is the ambition of this project? Well, we want to have a framework. We are not going to make a standard out of this project, but just a framework, scientific framework of different methods and tools. This framework has to be scientifically sound and evidence-based, and we need to ensure consistency across the models that we select and develop in the project. We want to try to have LCA models that model the reality as close as possible while avoiding normative choices. And then we need to have some tools that are highly applicable and are simple enough to be used in practice and work across sectors, and are also openly accessible, and then tested on case studies so that we know that they work or can work. That was mostly it from the project, and you hear more about our findings later today. And if you follow this link here, you can join our stakeholder network and be updated about new developments and new everything we produce from the project. And that was all. You can get in touch here with in Twitter, in LinkedIn, and in our website, and to me via mail personally. Thank you, and talk to you again later.
Thank you very much, Massimo. Yeah, we are very on schedule. Leo, if you want also to start introducing what is LCA and going now more into the core of our training, please, the floor is yours.
Thank you, Michele. Okay, can you see my screen?
Yes.
Okay. Oh, good. Good morning, everyone. So thank you all for joining that workshop. My name is Leo Staccioli. I'm working for the French Association Architect, based in Nice in the south of France. To give you a bit of my background, I have an engineering degree in environment, health, and safety. Then I quickly started to work in life cycle assessment studies. and environmental impact evaluation in general. So this is what I'm doing right now, mainly in European project like LIGNICOAT, where we're trying to identify the hotspots along the different value chains developed in the projects, and to provide some recommendation to the different partners to lower the impact as much as possible. So this was a quick introduction of myself. Now I would like to know a bit more about you. So I would like you to scan this QR code with your phone, or go directly on this website, slido.com, with this number. It's just for me to have an idea of your level in life cycle assessment. So I can maybe adapt my speech according to the results. So please go to this website, and I can see your answers in real time. Okay, so far it's quite well distributed.
I also share the link on the chat, so all the participants can enter.
Thank you, Rocio. Okay, let's just wait a bit more. Okay, so yeah, we have basically 1/3 of each level: beginners, intermediate, and experts. So I need to be really versatile in my presentation. Okay. So let's get back to the presentation. Okay, so we try, as Michele said, with a quick introduction of life cycle assessment. The slide that follow are just a quick reminder of the tool that we use to evaluate the environmental impact. So as we just saw, some of you are already familiar with it. That's why I won't spend much time on it. But basically, we can ask the following question: what is an LCA and why are we using it? The life cycle assessment is a standardized tool that follows the guidelines of ISO 1440 and ISO 1444. It allows to calculate basically the environmental impacts and the potential improvement of any product, any process. So we will consider the whole value chain from the raw material extraction until the end of life. Of course, we'll also consider all the intermediary steps like the production, the transport, etc. So in general, I would say that the LCA is a very specific analysis that is relevant and useful for a lot of people, from a research and development department to the marketing and sales. Yeah, basically everyone can use the LCA for different reasons. How does it work? So a life cycle assessment consists of 4 phases related between each other. We have the goal and scope definition, the inventory analysis, the environmental impact assessment, and the interpretation and conclusion. So the first phase is really important since we set the basis for the rest of the study. The question would be, what do we assess and why? So it has to be a clear goal, easy to understand for the audience or the readers. In this step, we also set the boundaries, which means what system will be under study, what are the limits. And so I won't get into the details, but if you're assessing a value chain, you can consider different limits. You can assess the environmental impact from the raw material extraction till the end of life of the product, but you can also only focus on the use phase, on production, or the end of life. It really depends on your goal. So in this phase, you also define what is called the functional unit, which is the reference unit for which you calculate the impact. So then we move to the second phase of the methodology, which is the inventory analysis and the data collection. So I would say this is the most time-consuming phase, since you need to get in touch with all the technical partners, investigate the literature, etc. So basically here we're collecting and quantifying all the inputs and outputs of the systems. So it includes the raw material, but also the emission released to the environment, the energy consumed, the waste, etc., etc. So all this data is collected for the functional unit previously defined. This is an illustration of the life cycle thinking and how to proceed to collect the data. So here you have a simple example with the plastic bottle and its whole life cycle, starting with the raw material extraction, which is the petrol to produce the plastic. Then we have the production, the packaging and distribution, the use phase, and the end of life. So as you can see, we have different possibilities for the end of life. The bottle can be incinerated, landfill, recycled, or reused. And of course, each route has a different impact. So as you can see, there is quite a lot of data to collect if you want a detailed and complete analysis. So then we move to the first step, which is the environmental impact assessments. During this phase, we're translating the life cycle inventory into the environmental impacts. To do so, we're using an impact assessment method or calculation method, which is one of the topics that we'll address this morning. And we're converting all this data into environmental impacts, such as global warming potential in kilograms CO2 equivalent, which is one of the most famous indicators, but you also have a lot of other impact categories. So to sum up here, we want to characterize the potential effects produced in the environment by the system we're studying. So to calculate this impact, yes, we have different softwares like CIMAPRO, Gabi, OpenLCA, and at Arditech we're using CIMAPRO and the EcoEvent database, which work pretty well. And finally, we jump to the last phase, which is the most interesting to my mind, since this is where we make the conclusion and where we can have an overview of the sustainability of our product. So this phase is called interpretation and conclusion. And here we'll try to present our results in a synthetic way, showing the main sources of impacts and the potential alternatives to reduce these impacts. All the results, yes, all the results are usually gathered in a report, and we provide it to the technology developers who order the study, and we can decide to take it into account or not. Okay, so this was a quick reminder about the LCA and the methodology. So now we jump to the first topic. So now we know approximately what is a life cycle assessment and how it works. We can go for scale up. So how do we scale up the data from lab to pilot or industrial scale? So this session will be divided into 3 sections, starting with a theoretical background. Then we have a practical example, and we'll finish with your questions. So yeah, since there are different levels of LCA practitioner, we try to make it understandable for everybody, and yeah, not be too technical. So I have another question for you before we jump into the subjects. I would like you to take your phone again and reply to this simple question. So it may. Sorry, I have to. Okay, I think now you can answer. So it's a simple question. If we take as an example the production of a bio-based polymer, which situation would generate more environmental impacts? The production of few kilograms at laboratory scale or the production of few kilograms at industrial scale? Okay. So we have more people going for the option number 1. Okay, this was more question maybe for the beginners, since it makes sense for the intermediate or expert in LCA. Okay, so let's keep these results in mind. Most of you say that the production of few kilograms at laboratory scale are generating more impacts. So let's see what it is in the following slides. Okay, so before diving into the examples, let's try to give you a bit of context concerning the upscaling data for LCA studies. So as I said before, the life cycle assessments are really important, are crucial for optimizing emerging technologies. From a sustainability point of view, you can, during this phase, you can identify different hotspots at research and development stage, such as the specific chemicals, the energy consumption, the raw material origin, etc., etc. So in consequence, we can say that emerging technology are often subject to high uncertainties and necessitate the scale-up of lifecycle assessment data. This will allow to reduce the associated impacts, which gives at the same time the answer to the previous question. So as you may know, we have roughly 3 scales, which are lab, pilot, and industrial scales. So at lab scale, we are usually using small quantities of materials. We're exploring the main characteristic of the new technologies. We're testing hypotheses and also the feasibility to scale up. This is also usually a more controlled environment where we can perform precise measurements. It's also cost effective and flexible. It's time efficient and safe. So there are a lot of advantages, but the samples are really small and let's say don't reflect the real world condition. Then we have the pilot scale study, which is a medium scale investigation with let's say semi-industrial settings. So here we want to optimize the process or the technology before we scale up to an industrial level. We test the feasibility. We also test the effectiveness of the current process, and we identify and try to address any issue that may arise during this research. So here we have realistic conditions, more realistic conditions. We also have larger sample size and a greater precision. And finally, the third one is the full-scale study, which is the industrial scale. So here we have commercial settings. We will evaluate performance, the reliability, and also the economic viability of our technology under the real-world conditions. So here we have larger sample sizes. We have a precision that increases as well, and also a longer duration of the process. So it can be, of course, a bit more expensive and long to put in place, but this is the highest scale that we can get. So these 3 scales can be divided into different TRL, which are the technology readiness level of a technology, and which allow to assess the technology's maturity. So it goes from 1 to 9, from the basic observation until the final product, which is bank financeable, let's say, on the market. The laboratory scales include the TRL 1 to 5, from the technology conceptualized until the prototype validation. Then we have the pilot scale, which include the full-scale prototype and the product certification. And finally, we have the industrial scale, which is the TRL 9, when the product is on the market. So as we said before, we're starting at lab scale, where we're studying the fundamental properties of the technology we're developing or the process we're developing. But this also means greater uncertainties. We have also lower efficiencies, lower level of automation, etc., etc. And on the contrary, when we reach the TRL 8, 9, and we get closer to industrial scale, we're reaching a high level of efficiency. We have a more mature technology. All the parameters are optimized. We have the maximum capacity and minimum cost. And we also have synergy effects in the process, which is really important, such as the heat, water, or energy recovery. So all this information leads to the following question. How does the TRL affect our LCA results? So if we take your previous answer to the question, what scale is generating more impact, we can say that most of you were right. We can say that the higher the TRL is for a product or a process, the lower are the impacts, which makes sense when you think about it, since everything is optimized. So this is well represented on this graph, with the curve going down as we're getting closer to the industrial scale. So once again, I would say that an LCA study of a laboratory process is really useful for evaluating the potential environmental impacts, compare the alternatives, identify the hotspots, also improve the production routes. But the laboratory process is also not optimized when it comes to life cycle assessment data. So with that statement being made, it becomes irrelevant to compare the results of a lab scale process with a developed alternative on the market. We'll get results that are not reflecting the real potential sustainability of a product under development, and this could lead to, of course, wrong conclusions. So this is why we need to scale up the data if we want to compare our product or our process to already developed alternatives. And in this case, it makes sense. Now that you have a bit of context, let's go for the main question and topics of my presentation. How can I scale up my laboratory data to pilot or industrial scale? So I investigated the literature a lot. I realized that this topic was widely investigated and that a lot of methods are existing. Some of them are quite easy to apply. Some others are really complex and require a lot of investigation, data, technical background in general. So the list that you're seeing is not exhaustive. This is a selection of 7 methods. And I will try to explain some of them. The 4 that you can see here: the simple extrapolation, the approximation, the process engineering, and the simulation. The other ones are quite complex and would not be, maybe not be relevant in that workshop. So let's start with the simple extrapolation. With this technique, we want to simply adjust our life cycle inventory or directly our results by using a certain factor and without complex calculations. This is the most important. So to do so, there is an important work of literature investigation. According to your product or your process, more or less data can be available. But this is necessary to analyze different sources of data, different modeling approach, different production volumes, etc., to make the relevant calculation. So for the simple extrapolation, we usually increase or decrease few values from our life cycle inventory, such as the material, the energy consumption, or the waste. Here we have an example in this graph on the right, which was taken from a paper where the authors wanted to identify environmental hotspots associated with the production of battery cell production. So this graph is an example of what kind of material could be used to retrieve data that allows us to extrapolate our inventory. So in this graph, we have the cell manufacturing energy demand in watt-hour per watt-hour cell energy storage capacity for different studies and for different production scale. So as you can see, this graph is quite similar to the previous one that we saw before between the impact and the scale of the process. Here there is a clear relationship between the production volume and the specific energy demand, which tend to be lower with larger production volumes. And if we want to go further, there is a need to retrieve a factor from this study that we could apply to our own assessments. But yeah, that was just theoretical, and let's say that this is the approach for a simple extrapolation. And as I said before, this was an example for the energy consumption, but there are other parameters that we can take into account, such as the material, the material waste, etc. So this was one technique. Oops, sorry. This is the second one. Let's move to the approximation. So with this methodology, we're using existing reference technologies and data to upscale our inventory. So this is a bit more detailed than the simple extrapolation, since we're considering both qualitative and quantitative description. In the qualitative description, we identify potential industrial production methods for our lab scale preparation. And in the quantitative description, we identify the, let's say, the future reactions and characteristic of our process. So here on the right, we have a schematic representation of information flow in the scale-up framework that we took from publication. And we have, as we can see, 3 analyses that we need to perform. The first one is the analysis of functions, which is a qualitative description of the protocol at lab scale. During this step, we identify similar procedures at industrial scale, such as mixing, stirring, etc. And we try to establish a connection between the laboratory procedure and the industrial process. So to give you an example, we have the stirring step in a lot of chemical processes, chemical reaction, which is often done with a magnetic stirrer and a Nerland-Meyer at lab scale. And at industrial scale, of course, we don't use this anymore, and this will be done in a tank of 10 or 20 cubic meters. So this is the kind of extrapolation we want to make and try to design the same process, but at industrial scale. So then we have the analysis of dimensions. The purpose of this analysis is to quantitatively describe the lab scale production and learn the process characteristics in terms of pressure, temperatures, yeah, all the parameters that you can find in this process. And finally, we have the analysis of similarities, which is the investigation of the properties and the characteristic of the similar large-scale process. So this can be the power requirement for the stirring. This can be other chemical transformation process, the yield of the production step, etc., etc. So in a nutshell, we have the analysis of function, which selects existing industrial process with similar function. Then we have the analysis of dimensions that provides info on the current reactions. And finally, we have the protocol at lab scale and the analysis of the similarities, which help to estimate the working characteristic at industrial scale. So this was for the approximation, which is another method to upscale our inventory. This one is maybe a bit more complex than the simple extrapolation, but it's still quite easy to implement and use for yeah, let's say a wide range of processes. Now we move to the third extrapolation technique, which is the process engineering. So this method is a bit more complex since we're using mathematical and chemical calculations. We have several authors that propose different methodologies to scale up the process and get the associated inventories. So the main objective here with this method is to provide different equations, different formulas that can be used to extrapolate to calculate the material quantities, the energy consumption, the waste, etc., etc. So I've investigated the literature, and I think one of the most used methods for upscaling data is the one created by Piccino. So in his work, he's identified several critical process parameters, which are really important when we scale up. So we're talking about the reactor size, the temperature, and the residence time. So in this paper, is providing different detailed formulas and calculations to determine the material, the energy flows, the emissions, and also the waste. So here's an example on the right. You have the formula to calculate the stirring energy that we talked about before. So yes, as we said, at lab scale, we usually use a magnetic stirrer and an LN layer, but when we want to upscale this at industrial level, we have to use a tank of several cubic meter. So with this formula, we're able to extrapolate an inventory and calculate the energy that we need, that would be consumed at industrial scale. So here we can see that we have several parameters that we need to know in order to make the calculation. We're talking about the dimensionless number, the density of the reaction mixture, the rotational velocity, etc., etc. So yeah, this method is also interesting, a bit more complex to implement since you need a lot of inputs to fit the calculations. But let's say this offers a reliable way to extrapolate your inventory. And the last method I wanted to talk about is the simulation. So I won't belong on that one since there is not a lot to comment, but basically in this case, we're using softwares such as Aspen or ISIS to simulate the change of scale, which is quite convenient when you can get some data on the process operation at lab scale. So the process simulation is a quite flexible tool to create life cycle inventories. And if we compare it to the, let's say, traditional data collection method, it's an alternative which relies on scientific laws such as mass and energy balances, thermodynamics, etc. So you have to know how to use this software. Okay. So this was a bit of theory before we go to the practical session. So here we have an example where we'll apply some of the methodologies that we just saw. As you know, we're organizing this workshop within the frame of two projects, LIGNICOAT and ALIGNED. And in LIGNICOAT, we are responsible for the sustainability assessments of the bio-based coatings, which are the final products. So we've been collecting a lot of data with all the partners, starting from the lignin to the lignin intermediates, then the bioresins, the bioadditive, and finally the biocoatings. One of the steps of this assessment was the synthesis of lignin-based polyols made out of lignin. So these polyols are compounds that are later used in the bioresin elaboration. And yes, this is the inventory. This is the inventory of this lignin-based polyol synthesis. So this was just a bit of context. So this inventory has been developed in the first place by Tecnalia. We defined the protocol, the quantities, the solvent, etc. And the same process was later upscaled by another company called AEP Polymer based in Italy. So we basically moved from a lab scale inventory to pilot scale. So in other terms, we could say from few grams to few kilograms. Here, as you can see, we have the flow on the left, we have the normalized amount per functional unit in the middle, and the equivalent process or proxy on the right. We also have some input that have been grayed out since, for confidential reasons, let's say. But basically, here we have the fractionated craft lignin, we have chemical, we have the solvent, which is the tetrahydrofuran. We have two other hidden chemicals, the cooling water flow, which is the tap water, the electricity consumption for each device used at lab scale. We have the rotary evaporator, the vacuum pump, the drying oven, etc. Then we have the output, which is 1 kilogram of lignin-based polyol ready to be used in polyurethane or alkyd resin. We have part of the THF, the solvent, which was consumed during the reaction, and we have the wastewater, which is uncontaminated since it's not in contact with the chemicals. And yes, finally, we have traces of remaining volatile compounds, which have been neglected in the study. So the objective with this inventory retrieved at lab scale is to first calculate the associated environmental impact, and second, to identify the input-outputs that are likely to change if we upscale the process. So these are the results for the global warming potential category in kilogram CO2 equivalents for the production of 1 kilogram of lignin-based polyol at lab scale. So we have a total of approximately 15 kilograms CO2 equivalent with 3 main contributors identified. So the first one in red is the solvent, the tetrahydrofuran, with almost half of the contribution. The second one in brown is the electricity with approximately 5 kilograms CO2 equivalent. Yes, just for information, it's an Italian electricity mix, which was used in the production occurs in Italy. And finally, the last significant contributor is the solvent treatment, the remaining tetrahydrofuran, which is not recycled at this point. So we choose the option of solvent incineration according to the partners. So this is the baseline scenario. We will use this inventory and the results to make the upscale and see how it affects our results. Okay, so now we move to the interesting part. What input or output from the inventory will change if we upscale the process? So we discussed with Tecnalia, with AEP. We investigated the literature a lot to evaluate how our inventory could be affected if we change the scale of the process. And in this case, we made a mix between a simple extrapolation and an approximation. We started to tackle the main contributor, which is the solvent, namely the tetrahydrofuran. So this solvent appears to be terrible for the environment, and its fabrication emits a lot of greenhouse gases. So we talked with Tecnalia and AEP to see if there was a possibility to use another solvent, maybe less toxic for the environment, but it was hard to keep the polyols properties with another solvent. So we tried to identify where the impacts was coming from, and it appears that it was mainly due to the butane 1,4-diol, which is an organic compound used to produce the solvent. So we investigated the literature once again, and we found the inventory to produce its bio-based version made of sugarcane. So we built the model in CIMA Pro, and we were able to get the impacts of the bio-based tetrahydrofuran. So if we get back to the upscale context, we could say that the industry could easily use this bio-tetrahydrofuran, this bio-based version of the solvent, given the current context and challenges related to sustainability. So this is one first change. We changed the solvents. Then, according to its technical sheet, the solvent tetrahydrofuran could be recovered at 90%. We can see here in yellow that the overall recovery efficiencies at plants where CHF is being recovered range from 85 to 97%. So we took an average of 90%. So this is something that is not done at lab scale, of course, but it can be easily implemented at higher scale, and it's usually done. Another important change is the water for cooling, which is thrown away at lab scale. So after a discussion with AEP, who was responsible for the scale up, the water would be recirculated in a circulator of this type. So this would change on one side the inventory for the cooling water, since it's now a closed loop. But it will also change the electricity consumption, since we need energy to cool down the water after use. So this is also something that we need to keep in mind. Then for the solvent removal, the distillation will be now performed directly in the reactor of the synthesis using a water-cooled condenser and a heat circulator, which will lead to less energy consumed. The electricity consumption in general will also be lower. We remove the drying oven and the rotary evaporator, which were energy consuming. And we will also adjust the electricity consumption for the stirrer and the vacuum pump according to their dimensions and efficiency if we upscale also the material. So this is something that we did also, thanks to the partners developing the process and thanks to the studies taken from the literature. And finally, we also made the last hypothesis, which is that half of the electricity could come from renewable energies, like biogas or photovoltaic production, It's quite common for industrial plants to have part of their electricity produced on site. So now we want to check how the upscale affects on one side my inventory and on the other side my results. So here is my new lifecycle inventory updated. We can see each input and output updated, highlighted in yellow. So the first input to be changed is the solvent. Now we have the bio-based THF, which was modeled and created in the database. The cooling water flow was deleted since it's now recirculated. We put 0 cubic meter because here the same water will be used to produce kilograms and kilograms of polyols, and at some point its impact will tend to 0. The vacuum pump and the stirrer energy consumption are lower. The energy associated to the heating circulator and the water cool condenser have been considered as well. The bio-based THF, the bio-based solvent is recycled at 90% now, so we only have 0.085 kilogram, which is considered as a waste. And we don't have any wastewater anymore. So now let's take a look at the results. So we have on the left the initial results of the polyols production at lab scale, and on the right the polyol production at pilot scale, let's say. So we can see that we have a very significant reduction of 76% for the global warming potential impact category. We can see that switching from classic solvent to its bio-based version is saving almost 6 kilograms of CO2 equivalents per kilogram of polyols produced, scaling up the energy consumption and adding renewable energy, also divided by 5 the associated impacts. And recycling 90% of the solvent also decreased the solvent treatment. So in general, we can say that our impact has been divided by 4 thanks to the upscale of the data. So this graph, this figure tends to confirm what we showed in the first slide. The higher the scale is, the lower is the impact. So of course, part of this environmental assessment include assumptions, hypotheses. Maybe it could be interesting here to make an uncertainty analysis and confirm that these results are close to the reality. So this is the conclusion of this presentation. So I think this decision tree for upscaling an emerging technology is a good summary on how to upscale data. So it was taken from an article, but basically we have 3 basic steps: the projected technology scenario definition, the preparation of a projected LCA flowchart, and the projected data estimation. So we start with a simple question: what will my new technology look like in the future? And from that question, I need to design an LCA flowchart. And from that point, ask myself different questions. Can I retrieve data for this upscale model? Can I make a simulation? Do I have access to software simulation? Is there a lot of data available on this on the same process at industrial scale? So I think there is not a single method that allows to upscale any type of data. There is a need to go case by case, study by study, and choose the most appropriate one. So yes, that's it. I think I hope this was clear. And don't hesitate if you have any question.
Hi, Leo. I'm just chipping in here because there are a lot of questions in the chat. So we're going to make selections of those and see if you can answer some of them. So there was first a question about one of the figure that you had back. I can't remember the slide number, but you listed all the upscaling methods in a certain order. And the question was whether these are listed in order of complexity. Yeah, this one, I guess.
So what was the question, sorry?
If these are ranked or listed or put in order of increasing complexity.
Yes. I try to classify them according to to the data you need and to the calculation that you need to put in place to extrapolate the data. So this was originally taken from another study, but then I also rearranged. So this is really subjective. Huh? I also rearrange the different methodology according to the one I found more easy to implement, let's say.
Right. Yeah, because I guess it also is a bit case specific. What will be the most complex case? You can have a general ranking, but then there are always specific cases where one method might be easier than another. If we stay a second on this figure, maybe there is another question which I think is quite interesting in regard to life cycle cost, and not environmental impact, but cost. What are the best options to conduct an upscaling? And I don't know if you can answer this, but are any of these methods useful also if you want to do a life cycle costing of an upscaling system, in your opinion?
Yes, because the life cycle costing is usually conducted in parallel to the life cycle assessment. It follows the same rules, the same it has the same functional unit, the same goal and scope, the same limits. So what we do, we usually convert all the environmental flows into economic flows when it comes to a life cycle costing methodology. So I would say that once we upscale the data for the environmental assessment, it's quite easy to make the parallel with the life cycle costing and upscale the data for the laboratory from the laboratory to industrial scale. But then you also have to take into account, of course, the equipment that changed. So all the capex, the opex that would change as well from laboratory to industrial scale. But in a general way, I would say that it's really correlated with the life cycle assessment. Yeah.
Okay, thank you. Then I think we need to move to the slide where you have both results compared. B23, yes, because there was a question here, and I guess is a clarification. Was such a high value expected for the carbon footprint of a laboratory scale?
What sorry, can you repeat?
The question is whether the such high value was expected for a technology at laboratory scale for this specific product.
To be honest, no.
Did you maybe compare with other products in the market when you did this screening here?
Yes, but that's what we said. It's not really relevant to compare these lignin-based polyols to fossil-based polyols on the market, since it's really well optimized, and the sustainability of the fossil-based polyol would be. I mean, the comparison would not be relevant in that case, since we have a product at research and development stage and a product on the market. But this is the whole point of doing a life cycle assessment in this research and development project. It's to give a feedback, to have an iterative process, let's say, so we can try different formulations. We can give a feedback in real time to the partners. So yeah, here that's what happens. We had this lignin-based polyol with a really high carbon footprint. So we could talk with Tecnalia, with AEP, to try to find a solution to fix this solvent problem, and provide some recommendation just to lower the impact and try to have a product with an impact as much low as possible. Yeah.
Thank you. There is another question here that I think is interesting. Can you discriminate or differentiate the influence of what are environmental friendly assumptions, for example, the green electricity or the bio-based THF, versus the upscaling methodology? So if we look back, you have a slide where you have listed all your new assumptions for the upscale system. I don't think it's this one, is
yes.
that one, yeah.
So can you repeat the question?
Yeah, if you can separate or discriminate the influence of environmental friendly assumptions versus what is upscaling as such. So pure upscaling, yeah.
Yes, understand. Yeah, this one is a bit optimistic, I have to admit. This is this is an assumption. This is an assumption based on what we saw in other studies and also our experience with the industrial partners that are producing their own electricity with photovoltaic units, with biogas biorefinery close to the plant. So yes, this is not this is an hypothesis. This is an assumption, but maybe you're right. We should separate this kind of hypothesis from the rest of the data, the upscaling statement. Yeah.
All right. Thank you so much. There are a ton of questions. I don't know how many we can cover, but let's see. Yeah, this question, shouldn't we use the medium voltage electricity we're scaling up?
That's a good question. Yeah, at large scale, I use low voltage, but yeah, I guess at pilot plant or industrial scale, we could use a medium or high voltage. Yeah.
Yeah. I should also say, maybe to your defense, that I mean, this is a very nice example that you presented here of how the process works. So you start with the system, with your data you have, and then you need to try to imagine an upscaled version. And of course, you make some assumptions, and this maybe needs to be discussed with some stakeholders, as you did as well. So you talk with industrial partners, you try to figure out what are the most sound assumptions. Then some of these are improvements rather than just upscaling, as somebody commented. But I think the point of example, I think, is really good. I mean, this really shows how the process works. And then, of course, the people in the audience may have a lot of questions or comments, or how to do one choice or the other, whether the assumptions are different and so on. But I think your point here was to show how in practice an upscaling works. And I think that worked really nice.
I can leave my email, and we can still be in touch if there are some questions. I can try to reply by email. Maybe it would be easier, since we don't have much time this morning.
I think there is another question here that could be interesting to take. So from your point of view, what results will give you an indication to continue scaling up a process or explore other alternatives in the early stages?
Yeah, that's a good question. I guess I don't know. It's hard to give up on the process. I guess the point is how to make it sustainable. It also depends. I guess it has to be oriented to the indicators you want to take into account. If you want to focus on the water footprint, on the emissions, on the human toxicity, trying to select maybe the indicators that matters to you or to your study, and try to make them as lower as possible by finding some alternatives. But I guess there is no process, such a terrible process, that you would say, okay, let's give up and start a new one. Yeah, the whole point is to find the good alternatives.
I think in previous projects where I've been involved, sometimes you figure out that some specific components or chemicals are really hotspots. So you start early on trying to substitute those, and this already make a big difference in the. So this is a really good information for the developers, because early on they can get an idea of, okay, where are we? You know, some materials that you use at lab scale, you won't be able to use a large scale. There are some questions about Aspen. Did you try doing the upscaling with Aspen for this, and can you share anything about that, if you did?
No, unfortunately I don't use Aspen, so I couldn't give a lot of information on that software. But I know that this is something that some LCA practitioners are using, of course, and I guess it's really useful when it comes to upscale some data. But I don't have a lot of experience in simulation.
Yeah, we have done something like that with Aspen. We have a paper under review about this, and there are some questions here. It cannot simulate like major changes in the structure of a system, but can account for all the efficiencies and the energy savings and these things, including the energy use and reagents use and so on. So it can be used, but it's quite complex to model if you're not Aspen expert.
Mm-hmm.
Let's see if I can. We have how much time we have? We have still some time, right?
Like 10 minutes.
10 minutes. All right. Let's see. This one. How did you decide the parameters and conditions for the industrial scale? I mean, you're also making assumptions about the industrial project.
I don't understand this one. How do I in this specific example or?
Yeah, I think so. In this specific example.
So this was just communicated by the corresponding partners who upscaled the process. Otherwise, this is the second technique I was talking about. The approximation, so where you have to investigate the literature and find some similar processes that could match your lab scale protocol and adjust the characteristic, the kinetics of your reaction. But otherwise, if you have a direct person to talk with, it's the easiest way.
I think you mentioned also before that you've been talking to your industrial partner and trying to understand how this will look like in a bigger scale also as first thing. So you are in the privilege or good situation where you can have a direct contact with people who are going to implement this in a industrial context, so they know already what to expect. So your assumptions are grounded in some domain knowledge, I would say. Let's find another question here. There is a question on why you use the cutoff version of the database. Any specific reason for that?
No, it was just I don't have any specific reason for that. I know that cutoff is quite a simple way to consider the different data in the lifecycle inventory, since we're not considering all the recycling park, etc., etc. But no, I don't have any specific reason for that.
All right. There was a question about the waste. So the impact of the waste, how has that been considered? Is the fractionated lignin a waste flow? And how has that been considered in the scale up as well?
Can you repeat?
Yeah, the impact of waste, how that has been considered. So you have an input of some waste, you said, probably the fractionated lignin, and how has that been modeled, and especially how, if there is any consideration in the upscaling regarding the use of waste?
So I don't have any waste related to the fractionated lignin. It's consumed during the reaction. So the only waste that I have is the solvent, which is a solvent and a reagent in the reaction. So part of it is consumed during the reaction, and we have this as a waste, and we also have some traces of remaining compound that are neglected. But no, I don't have any ways regarding the fractionated lignin, not for this process. So we are starting with the craft lignin, which is then used to produce this fractionated lignin, but this is another process.
Okay, also another question here is, this has not too much to do with upscaling, but maybe we can discuss that. Is your analysis aligned with the PEF guidelines? Product environmental footprint is PEF.
Is my analysis online?
No, aligned or is done according to the PEF guidelines.
So yeah, PEF guidelines is the framework. So we didn't follow specifically all the rules of these standards. So the main standard, let's say, is the ISO 1440 and 1444 of the life cycle assessments. But I guess this could be interesting to check if our study complies with all the PEF framework, which I think it was still under construction, but yeah, no, for this study, no, we didn't.
Maybe a twist of this question is whether do you know if in the PEF there is any consideration regarding the LCA of upscaled, making an LCA of an upscaled version of a technology. Do they have any recommendations there? I don't recall that, but maybe
no, I don't think so. I don't think so.
No.
Mm.
But these are guidelines about doing LCA in general, so they will apply whether you do it at pilot scale or large scale or industrial scale. Let me see. Maybe this question. So you have presented a lot of different ways to do the upscaling, the foreground system. Is, to your knowledge or based on your experience, any of those who are particularly fit to the case of bio-based technologies or products? I'm just interpreting a question here, which is, yeah.
Yeah, this is really specific. If one of these methods would fit more the bio-based sector.
Yeah, exactly. That's the way I interpret this question here.
Yeah. To be honest, I don't know. I don't think this is a question maybe of sector, but more about as I said, your data availability at lab scale and data availability in the literature regarding your process and according the method you choose. If a lot of upscale process for your bio-based product are available in the literature or data available thanks to industrial partners, this is really easy to implement any of these upscaling methods. But I don't know if, for example, the approximation method or the process engineering method is the best one to apply to this sector. I don't know if we can make a generality of this. I guess we have to go case by case.
Great. Thank you. I think I'll take the last question. This is, then we need to give you a break as well. But that's quite interesting one. In fact, how can we take into account the supply chain challenges when upscaling a process using bio-based materials? For example, how can we ensure that there is enough sustainably sourced biomass available? And if we know there is not enough available, how do we reflect that in our model? Do you have any thought about that?
Yes, the feedstock, indeed, is really important. The feedstock availability. So yeah, I guess you also have to make your own investigations. Yeah, for example, we are working with the the lignin here. So we were starting with craft lignin, organosolid lignin with few kilograms. But then, yeah, if we want to upscale the process, I guess we will need tons of lignin. So it will have an impact on the price, on the environmental impacts, and also on the availability, I guess. Yeah, you need to definitely take this parameter into account, and maybe talk with some providers. Maybe we have some industrial lignin providers for this project. I've been in touch with them to try to get inventories and the way they were producing this different kind of lignin. So I guess this is a question maybe that they could address.
Thank you. I would add that this is a really important aspect, but it's not very, LCA is not very well geared for addressing this topic yet, because it deals a lot with flows and not a lot with stocks. We have been working in the ALIGNED project to try actually to solve this using a sort of more consequential approach and looking into the constraints to the biomass, but maybe I'll show you something later or put a link there. But this is not very well covered by LCA right now. And it's definitely interesting to consider. Maybe very last question, since we have 2 minutes. There is a question about sensitivity analysis here. Have you tried doing sensitivity analysis on the upscaling assumptions?
Not for this one.
But if you had to do it, how would you do it? Maybe if you could give an example to the audience.
So actually, we're actually writing a paper on this one. So I have a colleague of mine who has performed a Monte Carlo analysis about the different data that we just saw in this life cycle inventory. So I guess the Monte Carlo analysis is one way to do it. I don't do it myself, but this is something that is integrated in general in the software like CIMAPRO. You can also so this is for the uncertainty analysis, but we can also make a data quality assessment. So it's quite different, but still it has to do with the data. So it's a kind of matrix where you classify the quality of your data according to the geographical, technical, and I don't remember the third one, representativeness, and you get a score, and you can see if your data is quite good, fair, very good, or quite bad. So this is for the data, and for the uncertainty analysis, we should perform. Ideally, we should perform an uncertainty analysis for each LCA study to see how reliable is our data and our results.
Welcome back. I think we can continue with our agenda. We are very on time. So now we will have also other 2 relevant sessions. One is on calculation methods, again will be Leo presenting, and then we will finish with the accounting of carbon, and there will be Massimo presenting here. So yes, please, Leo, feel free to start sharing. And I remind anyone to use the Q&A box to make your question.
Okay, thank you, Michele. So now we move to the second topic, which is about the calculations methods, or what we also call life cycle impacts assessment methods in LCAs. So here we'll follow the same structure as before. We'll start with a bit of theory, explaining what is a calculation method. Does it exist different ones? What are the differences, etc.? And then we'll try to put the theory into practice with a small exercise, as we just did, for you to have an idea of how it works. Yes, finally, we'll keep 5 or 10 minutes for the question. Let's start. Let's start with the first slides. So what is a calculation method? When we say calculation method, we have to take into account that it happens in the third phase of the life cycle assessment, which is the environmental impact assessment. To keep it simple, the calculation method allows to transform the raw data that we collected in the previous step, like material, energy, or waste, into different understandable impact scores. So in other words, they will quantify the environmental impacts of our processes, of our product that we're assessing, and allow the client or the partners to take some measures to lower their impacts. So there are quite a lot of LCA methods, and we choose a method according to different factors, such as the set of impacts that we want to consider, the country where the product or the process comes from. So there are different parameters to consider, to take into account. For example, if we want to focus our study on water impacts, we will use a water footprint methods. If we have US clients, we will choose the Tracy method, which is the one used in the US. So we have to choose the relevant one that fit the context of our LCA study. So now we know what is the calculation method. We can also ask the following question, which is, how does it work? So as you may know, there are different softwares to calculate the environmental impacts of a product or a process, like CIMAPRO, Gabi, OpenLCA. And all of them includes different calculation methods, which are scientific tools to calculate the environmental impacts. So if we just take an inventory like the one we saw before, it's really hard to tell if this system, if this product is impactful or not. So we need to translate all this data, like the resources, the electricity consumption, the waste, etc., into numerical values. To understand how it works, we need to consider two things: the impact categories on one side and the impact factors or characterization factors on the other side. The calculation methods will take into account different set of impact categories and different substances. So for each impact category, we have different substances, and they are multiplied by what we call the characterization factor. And the results expresses the relative the contribution, let's say, of each substance. So let's take an example to make it easier to understand. For example, here we have a screenshot taken from CIMAPRO. So you have the impact category on the left, you have the substance in the middle, and the factor on the right. So the first thing to know here is that for the global warming potential, the characterization factor for CO2 is equal to 1, since it's the reference unit. But if we take the characterization factor of the methane, for example, it's 25. What does it mean? It means that if we release 1 kilogram of methane, it's responsible for the same amount of climate change as 25 kilograms CO2. So that's why we're talking about kilogram CO2 equivalent. It's because CO2 is the reference greenhouse gases for global warming potential. Yeah, quick slide about impact category. Talking about them, I wanted to highlight quickly some of them that we're using quite often. So in a nutshell, we can say that there's sort of KPIs, key performance indicators, that will allow the comparison with the other product or process. We could define after that which one is more interesting from an environmental point of view. So the first one is, let's say, the most famous. We just talked about it. It's the climate change potential expressed in CO2, kilogram CO2 equivalent. So it's an indicator of potential global warming. due to emissions of greenhouse gases to the air. And we can see directly the consequences with the rise of the global temperatures year after year. So then we have the acidification, which is the indicator of the potential acidification of soils and water. We also have the impact of toxic substances on freshwater organism with eutrophication. We have the enrichment of freshwater ecosystem, which is still eutrophication. Sorry. Yes, so we have different impacts in the land use, which is the last one, which measure the amount of land that is occupied for a certain period. So these impact categories are quite common and are usually included in a lot of LCA methods. Sometimes the unit can be different for the same category. We'll see that later in the next slides. If we take, for example, the resource use, it can be expressed in kilogram oil equivalent or in megajoule. The acidification can be expressed in SO2 equivalent or in mole H+ equivalent. So there are several differences according to the method. Okay, now the following section will focus on the different life cycle impact assessment methods that are commonly used around the world. So there are quite a lot, as you can see in this non-exhaustive list. Some of them focus on specific impact categories, specific sectors. Some other are tailor-made for the country where they've been created. So there's quite a lot of choice when it comes to choose a method. However, for this presentation, I decided to focus only on these 4 ones, which are widely used in Europe and around the world. So I choose to introduce the European LCA method, which are the environmental footprint version 3.1 and the EN 15804, which focus on the construction sector. So then we'll review quickly one of the most used calculation methods since it's global. I'm talking about the recipe 2016. And finally, we'll finish with the US LCA method, which is Tracy. Okay, let's start with the environmental footprint version 3.1, which is the calculation method that I used in most of my studies for European projects. So this method is harmonizing, let's say, the environmental impact assessment across Europe in non-construction sectors. This is important. This is for the next method. And this method allows to compare a study conducted in Germany with a study performed in Spain. So this is actually recommended by the European Commission itself, since it has been initiated by the Joint Research Center, which supports EU policies. The overarching standard is the PEF, the Product Environmental Footprint, which is a framework we were talking about before. And the last update, if I'm not wrong, is for 2022. Now we move to the second European calculation method, which is the EN 15804 plus HU, which is based on the same European standards dealing with the sustainability of construction works and also the rules of the environmental product declarations. So it has been initiated in 2012 by the EU and has evolved year after year. So we have different versions since 2012. So this calculation method is really relevant when you're assessing the environmental impact of a product or a process dealing with the construction sector. And it can also, of course, be used to perform an environmental product declaration or EPD. Just a quick parenthesis about the EPD. So it's a document which exhibits the environmental performance of any product, any material during its lifetime. So it's really used in the construction industries because it allows to compare the impacts of different materials or products. And it's quite useful for architects, engineers. We can choose the most, let's say, sustainable options for their project. So it's usually valid for 5 years, and it looks like this. Okay, so it's usually a few pages. It's basically a summary of a life cycle assessment, and you can find more information on the website EnvironDeck. Okay, so this was for the construction methods. Now we move to a global life cycle impact assessment method, which is Recipe 2016, and which is also widely used around the world. So let's start with a quick description of this method. This Recipe 2016 offers both midpoint and endpoint indicators. So here I also want to open a parenthesis to clarify what we're talking about when we say midpoint and endpoint. So when we're talking about midpoint indicators, we're talking about the immediate environmental effects, such as the emissions or the resource use. And when we are talking about endpoint indicators, this is about the long-term consequences, like the damage to the ecosystems or the biodiversity loss. So to give you an example, if we consider, for example, a toxic chemical, which is emitted in the groundwater by random industry, at some point this chemical will end up in the lake, where its concentration will increase and might reach a dangerous level. So this is the midpoint indicator. And the consequence, direct consequence, would be the fishes will start to die. So it might provoke their extinction. And this is the endpoint indicator. So to come back to our calculation method, this gives the choice for the LCA practitioner between a detailed analysis or a more simplified one. This method was, of course, designed for a wide audience, such as researcher, policymaker, industry, etc. And it was created by the National Institute for Public Health and the Environment, together with several universities. And finally, the last method I wanted to talk about is the TRACY, which means Tool for Reduction and Assessment of Chemicals and Other Environmental Impacts. So it is a set of characterization methods that were developed by the US Environmental Protection Agency. The objective of TRACY's method is specific for conducting LCA, but it can also be used for other uses, like the prevention of pollution, especially in North America. So I don't really use this calculation method since it's more appropriate for the American context, but it's still widely used, so it makes sense to have a word about it. So in this slide, I wanted to show you how the assessment can be different from a method to another. Here, I decided to assess 1 kilogram of polyethylene terephthalate with 2 different life cycle impact assessment methods that we just saw, which are the Recipe 2016 and the environmental footprint 3.1. So what we can say at first glance is that we're not considering the same impact categories for the two methods. On the left, for the environmental Recipe method, we have a set of 18 impact categories. And on the right, for the environmental footprint, we have a set of 24 impact categories. So for example, on the right, the climate change category is declined into 3 subcategories, which are the climate change biogenic. So Massimo will talk about it right after this presentation. We also have the fossil, and we also have the land use. So now if we take a look at the values, we can also say that they're slightly different according to the method. If we take, for example, the global warming, so this can be explained by the fact that methods have different parameters or allocation. The Recipe method also consider global average when the environmental footprint is focusing on Europe. So this might lead to different values sometimes. Another impact which appears to be different is the water. So on one side we have 0.018, and on the other side we have 0.7 cubic meters. So here it's important to look at the name of the impact category, we have water use and we have water consumption, which is different. The water use is the total amount of water taken from its source that we're going to use for the process. When the water consumption is the quantity of water that we use and which is not returned to the original sources. So there is a difference in the definition. That's why we have a different value as well. So then we also have different units for the human toxicity. One is expressed in comparative toxic units, the other in kilogram of dichlorobenzene. The resource use is divided in two subcategories for the EF method with fossil and minerals and metals. The land unit is different. So yeah, here we can see that it's really important to choose the relevant method for our study because the result can be quite different. And finally, what I wanted to highlight is that when we compare two studies together, it's also important to check the method that has been used for both assessments, so we can make the comparison relevant. Okay, so now I would like to do a small exercise with you. So it's really easy. Maybe it makes more sense for the beginners. But still, everyone can do it with its calculator on his phone or laptop. But basically, I would like you to tell me what product between 1 and 2 has the highest environmental impact in the global warming impact category. So I think you have everything you need in these slides. And let's take maybe a couple of minutes. I will put the alarm. Okay, let's take 2 minutes. Thirty seconds. Okay, so let's go back with our phone, scan these little QR codes to get your results. I don't know if you had time to scan the QR code, sorry. So what product is the most impactful in the global warming impact category? Okay, so there is almost everyone for the product number 1. Okay, a few more seconds. Okay. Well, yeah, good job. So the product number one was indeed more impactful. So we just had to make a simple multiplication between the characterization factor and the different substances. So we have 5 for the product number 1 and 3.87 kilograms CO2 equivalent for the product number 2. So basically, we just did the job of CIMA-PRO by calculating the environmental impacts of a product. We can put this in place in more complex Excel files. But this inventory was quite simple. Of course, with the other value chain more complex, we need the software, or we need a more complex Excel files, Excel model. So this was a small exercise to show you how it works, and I think I'm a bit ahead of schedule, but this is my conclusion for this second topic. What should I keep in mind regarding the calculation methods? So first of all, we need to know that the calculation methods categorize and quantify the environmental impacts of any product, any process. They're a useful scientific tool that allows us to convert data that we previously collected into numerical values. So we're talking about the material, the energy, the waste, etc. All the data that we find in the life cycle inventory. This is really useful, of course, for the practitioner. So we can propose recommendation or mitigations measures to lower these impacts. We saw that there is a wide range of calculation methods that have different set of impacts, characterization factors, which are specific to a region or a sector. So it's pretty important to choose a relevant method that matches the requirements of our study. It's also important to keep in mind that calculation methods have an influence on the LCA results for the reason that we saw before. So yeah, just check before comparing two studies that if the method used was the same, or if we perform the same study, use the same calculation method to get the same results. And yes, so it's kind of important to understand all these parameters, to take them into account to choose the right method for our assessment. Okay. So I think that's it for this second topic.
Should we look a bit at the questions? Or not as many questions as before, but maybe more will come. But first of all, there was a question of what method was used in the previously shown case? The one, I guess, the exercise we're referring to?
It was the environmental footprint 3.1, the one that I just showed. Yeah, because it's the one recommended by the European Commission, and it's a really detailed calculation method. It also follows the framework of the product environmental footprint, and it's specially designed, let's say, for the European context. So it makes sense in this kind of European projects where all the partners are coming from different countries in Europe to use these methods. Yeah.
Thank you. Yeah, there is a follow-up question on that. How can you address the issue of global warming associated with CO2 and CO biogenic in the environmental footprint 3.1 method, considering the factor is set to 0 for emission to air? I don't think that was to 0, right? Or maybe for CO2 biogenic was to 0.
It's usually -1, right?
Yeah. Otherwise, you will have almost no results here. But yeah, What will be the way to check that?
So this screenshot is quite old, but yeah, it should be it should be a negative value for the biogenic carbons. It's supposed to be a credit. But yeah, don't take this slide into account. This figure, I mean, the screenshot.
Yeah, this just shows what is that? That is
yeah.
Oh, polyethylene, yeah. But to look at that, you should open the method and check the characterization factors themselves. I don't think you have a slides about it. But also to answer this question, I have also slides about this later. So if you can wait a second, we'll come back on this point of the biogenic and the characterization factors. Another question, there are a couple of questions on EPDs. I guess because you mentioned that. So is EPD for the construction industry only, or is it broader applications? A more broad question than just about this presentation, but since we don't have a lot of questions, we can take it.
No, EPD can be applied to other sectors. Of course, it's particularly useful in the construction sector, since it's yeah, the laws engineers or architect to choose between different products. You have like one sheet with clear impacts of your product for 1 square meter of insulation material, one concrete, bio-based concrete, 1 brick of bio-based concrete. So you can compare the different materials and have choose in an objective way which one is the more sustainable. But you can apply this to other material than construction sector.
Thank you. Then somebody here has confirmed that Damien has confirmed that environmental footprint 3.1 has a 0-0 approach. So biogenic carbon is not included in this. So we can take this later again in the next presentation about what to explain what a 0-0 approach is. Let me find the other question. Just a second. We are just bumping up all these questions. Yeah, there is one question: to measure the carbon footprint of a construction product, what guidelines are better to use, ISO 14067 or the EN 15804? I'm not familiar. I'm not into the construction sector so deeply that I can provide
Which
an
one?
answer to that. ISO 14067 or EN 15804.
I only know the second one as well, since it's the same standard that has been used to build these calculation methods. So yes, I'm not familiar with the first one, but yeah, for the construction sector, I guess the reference is the EN. Yeah, but I couldn't make I couldn't tell which one is better.
Is the one about carbon footprints, the 14067. Carbon
Okay.
footprint of products, requirements and guidelines. I think it really depends on what where you have to use your LCA. If you need to comply with VEN, then you need to use that method. So if you sell a product where this certification is required, then you need to use that guideline. Otherwise, you can use the ISO, of course. The same for the EPDs. You have to use the guidelines that are specified in these specific category rules. If you want to have an EPD certification. Other questions? So there is how the landfill waste lower CO2 emissions compared to incinerated? This is a question about the data that you have there in the figure, but I guess you took them directly from Econvent, right? The activities,
Yes.
the data sets.
Yes. So apparently, yeah, landfill is quite terrible, since then it also emits a lot of CO2 when the let's say the material is degrading itself. But I recently learned that in the EcoInvent process, this landfill process only take into account the transport. Let's say in the landfill area in the plant, so all the logistic between the different trucks, etc. But it doesn't take into account the process itself of the material being landfilled and what happens next. So that's why it's that low. It's because I think it only considers the transport in EcoInvent.
All right. Yeah, there are a lot of comments on the environmental footprint 3.1 that the 0-0 approach, and that means that the biogenic CO2 is not included. Fine, but I think this we can take also later because it's all the same issues, right? But I guess the point here, what do you do if two different methods have different approaches to account for the carbon, the biogenic carbon, for example?
What do you do?
Yeah, what will you do? Or what are the things that we have to be careful about, maybe?
Yeah. So yes, it really depends on your approach as well of the biogenic carbon. I know it's quite subjective according to the LCA practitioner. Some of them see them as credits that you can apply to your results, but some others say that yeah, for example, if you take a table made of wood, so these woods will generate some biogenic carbon and potentially some credits. But if we go until the end of life of this table, this carbon would be emitted again in the atmosphere. So this is something that you can also take into account in your study. So there are different approaches. I guess that there is not one single method which is valid, but concerning the calculation methods, yeah, it depends on the LCA practitioner, let's say subjective opinion, yeah, on how he wants to implement that impact category in his study.
If I can add to that, I think the point of your presentation was really clear that there are a lot of different methods available and they are different. So if you use one or the other, the result will be different, very likely. Maybe the overall interpretation could be the same, but the numerical values might be really different. Or, maybe not all of them, in some categories, in some other not. So it is really, the results are really substantially depending on the method very often. And for the greenhouse gas impact, climate change or global warming impact, depending on the method, how we call it, it is very important that we are aware of the assumptions behind the method. And especially if you, as you said, if you compare your own product or your own study with another, you need to make some choices regarding the method that are similar. So if one method has used if one study has used one of these methods and you use another that have different assumptions regarding the carbon, then you get results are not directly comparable, and this can be very misleading. Misleading, but you may not be able to compare these things properly because some impacts are not accounted for or are not considered impact. So this is really, when you look at if you compare your results with those of somebody else, always check what method they use and in great detail and try to use the same. The problem is that some people don't even write what method they used, and this is also doesn't make things easier. So my recommendation is also to really be clear, reporting the type of method used in great detail, what version, what name. I don't know, there are a lot of questions about the biogenic carbon, but I would prefer to take them later maybe, because we have a presentation about that. Let me see. There's one that I don't understand here. In general, maybe this one, what is generally challenges when using in the impact assessment phase when you compare bio-based processes versus fossil-based processes?
What are the challenges?
Yeah, in terms of impact assessment. Is there anything particular we should be careful about or attentive to?
Yeah, it's a good question. So, yeah, I would say first is to define a good benchmark. Yeah, like products that are really comparable, that have the same function. Usually, yeah, when it comes to build inventory of fossil-based alternatives, it's way easier since a lot of inventories are already available in the databases, in the literature, etc. Bio-based material, you have to struggle a bit more, of course, but this is what is interesting. Then what are the challenges when we compare bio-based and fossil? Yeah, no, I would say define the good benchmark and build the inventory for the two of them, a solid inventory that allow the comparison. Yeah, no, I don't have any more thoughts on that.
Thank you. I think when we have answered that, I think the other questions are more or less on the same topic. I will stop it here, Van. How are we with the schedule? We still have 10 minutes. Rasha, what do you say?
I mean, we can start with your presentation right now if you want, and then we can have more, like, couple of minutes for Q&A.
Okay. Yes, then I will share the screen. Let me see. Thank you, Leo, first of all, for the presentation.
Thank you very much all for your question and your attention.
I think it's this one. Can you see presentation mode now?
Yes.
All right, so good morning again, everybody. And let me just remove a couple of windows here. So I'm going to present a bit of the work done in the ALIGNED project on accounting for the impact of carbon emissions in bio-based products and what the ALIGNED framework is about. So I'm presenting this work today, but this work has been a collaborative effort, and in particular led by Laurie Hamelin at INSET together with Damien Arbault and Hugo Javures. not sure how to pronounce it, sorry. So that's the people who really contributed to this study and that I'm presenting the results about. So a little agenda first about modeling biogenic carbon in LCA, and then about modeling carbon dynamics in LCA. And then we'll look into the aligned modeling recommendations, so how to do this modeling the way we think is most sound. And then what are the tools available for doing that that are part of our deliverable 2.1. And I'll tell you where to find all these materials. So I would like to, it's not a disclaimer, but I was informed that we were aware that a lot of people in this audience might have been CA beginners. So this presentation is targeting a bit of everybody, but including the beginners. So for the more experts, there might be some repetitions, but I hope you can bear with me. So let's talk about the biogenic carbon. Okay, how to account for that in LCA? First of all, biogenic carbon is defined as the carbon from biomass and its transformation, which is usually there is like a dualism. There is the biogenic and the fossil. The fossil is the one from the carbon that has been in the soil for a very long time. And then we need to make a difference between the accounting of carbon flows that is done usually in the inventory phase of an LCA, and Leo has been presented the 4 phases. So you should be, if you recall, that is where you account for all the material and energy inputs of a product system. And then there is the accounting of carbon impacts, which is what also Leo has just been presenting. So the impact assessment phase of a life cycle assessment, where you you multiply the inventory results by the characterization factors. So different combinations of the two things can give the same result. And let's have an example here. So for example, I have a negative input of minus 10 kilo of carbon dioxide fossil. So you want to model a carbon uptake, and you could do that in a software. You have a flow called carbon dioxide software. You want to model uptake, you have a negative input. And then you use a positive characterization factor of +1 kilo CO2 equivalent per kilo CO2 fossil. And you multiply the two just you did in the previous exercise. And then you're going to have another combination when you have a positive inputs of +10 kilos of carbon dioxide biogenic that could also be used to model a carbon uptake in your software. And then a negative characterization factor for this exchange of -1, this time, kilo CO2 equivalents per kilo CO2 biogenic. And then in both cases, you will have the same result of -10 kilos of CO2 equivalent. Now, so this is just to show that we need to distinguish the two concepts, the accounting of inventory flows that can be done with positive, negative numbers, but also selecting different names, different type of exchanges, and then the characterization factors in the method, in the life cycle impact assessment method, but also have positive and negative characterization factors for different types of exchanges. Right. So the main approaches for accounting biogenic carbon, we have already mentioned 2 of them. We have mentioned them slightly in the previous question answer session. So are the 0, and +1, -1. So what is the 0, approach that we have just seen is used, for example, in the environmental footprint 3.1. So all the absorbed and released biogenic carbon is accounted with a characterization factor of 0. So it doesn't, it's not counted in the global warming potential, in the global warming impact in a way. When you have sequestration, then you have a characterization factor of 1 and a flow accounted as a minus. So this is to model the permanent sequestration of carbon. What are the main issues when using this method? So you induce the idea, or it's based on the idea, that there are no climate effects from the use of biomass, because I mean, it's a bit put in a negative way here, but it's based on the idea, which is also justified, that biomass as a sort of renewable cycle. So all the carbon that is uptaken in biomass is also released in a sort of human time frame. although this is not always the case. It is the case for many processes, but not for all processes. Important CO2 flows are invisible in the results, so you can't track them. As we were just seeing in this example before, we have an impact calculated, but the carbon, by budgeted carbon, is not included in this number, so it cannot be seen. This can affect the way you make decisions. And then you can have mass balances that are distorted when carbon is uptaken CO2 but released as another gas, or not reabsorbed necessarily. And then when you have temporary storage, so it's the same issue as before in a way, if you uptake the carbon and then keep it in the technosphere for a certain time and then re-emit after, you cannot see the difference between these two things. What about the other approach is the +1, -1, +1. So you can have an uptake from the atmosphere counted as a negative. So, for example, you could have a positive inventory flow and a negative characterization factor, and vice versa for release. So the combination depends a bit on how you match the inventory and characterization factors, but the whole idea is that uptake is with a minus, release with a plus. And only net flows are accounted, so no sequestration included, because everything is accounted already. What are potential issues? Well, you need to keep track of more flows, so it's potentially more difficult, more data needed. You could have, this is important, potential misinterpretation of results if the system boundaries of your system is cradle to gate. So if you produce a product and this product is bio-based and is based on biomass that has been uptaking carbon, and then the LCA stops at the gate, so your functional unit is a unit of product, but you don't include what happens afterwards in the use stage and in the end of life where this carbon is released again. So in this case, you will have a carbon negative product. You might have a carbon negative product. However, this is not carbon negative necessarily in a life cycle perspective, but only in this part of a life cycle. So this approach combined with this type of model is, or system boundaries, I should say, could lead to some misleading results. Another issue potentially is how to really account for these absorptions. So how much CO2 is, let's say, uptaken by producing a bio-based product. One approach usually is to take the carbon content in the product and then convert this in the amount of CO2 uptaken. However, this could be underestimating the total uptake in a way, because there is carbon that is maybe absorbed in the biomass but not included in the product due to either conversion losses or because it is below ground or other reasons. Also, it can be based on the NPP, net primary productivity, or the crop yield, but as I recall, this is also quite complex to do, or at least there is not a one unique way of doing it. Here are non-exhaustive list of how different guidelines use the different approaches. This might be a bit old, but you can see basically the point is that, and as we have seen also in the previous presentation, different guidelines use different approaches. So coming back to before, it's important that if you use one method or another, you know exactly how this method is accounting for carbon. And if you compare yourself with a study, your study with a study that has used another method, then these results might not be directly comparable because of these choices done in the method. Right, so that was about the biogenic carbon. Now we move to another topic, which is the modeling of carbon dynamics in LCA. So the topic is about the time dependency of a climate impact. So when you have an emission of greenhouse gases, this has an impact, and this impact depends on when this emission is emitted, basically. A standard approach in LCA most used in, I would say, 90% of LCA studies, 95, 99. Most LCA studies use a steady state rational, so time is not considered. So all emissions over the life cycle happen at the same virtual time. Okay, so if you have production of a product, laptop, could be any product. Production is yesterday, use is today, and end of life is tomorrow. The emissions that happened yesterday, today, and tomorrow, they are all happening at the same time in LCA. In the normal LCA, let's say. So time effects are disregarded. Also, the impacts, as you've seen in the partly the previous presentation, the impact of greenhouse gases is assessed over a given fixed time horizon, for example, 100 years. This is why it's called, for example, global warming potential 100. And I'll come back to that in the next slide, because the time horizon for calculating the impact of these greenhouse gases is 100 years. But you can also have GWP 20 or GWP 500, so different time horizons. If you instead move to a dynamic approach, then you will have a CF is a characterization factor for each year of emission. In a way to reflect the amount of, I'm talking about greenhouse gases, the amount of impact, cumulative radiative forcing, that each emissions have from the time it is generated or released to the time horizon chosen. So if you emit an emission at year 30, then it will be the impact from year 30 to year 100, if 100 is your time horizon. By doing that, this is a more detailed accounting of all the impacts, and requires that you have an inventory and that is time specific. So for each year, you should know how much emissions you have, and also characterization factors that are time specific. This in practice means that emissions occurring earlier are given more weight. This is not a weighting procedure, so weight is not the right term here technically, but just so the impact. This is based on the idea that whenever you have emissions, you have impact, but if you emit before, you will have more impact in a way. I'm taking as an example to explain this an old paper from 2010 that talks about the concept of pulse emissions and cumulative radiative forcing. So let's look, this is from Levasseur in 2010. It's old, but still good, pedagogically good and valid, of course. So you can see in this chart here that this is the impact of different greenhouse gases. You have carbon dioxide and methane. And carbon dioxide is the black line here, and the black continuous line, and then methane is the black dotted line. So this is how much radiative forcing per unit of mass, so basically the climate impact in a way of the greenhouse gas over time after emission. And you see that these two gases have very different profiles. Now, if you look at the equation for calculating the global warming potential, it is a ratio between two integrals. So it's basically the ratio between the area of this curve, so the cumulative, that's why it's called cumulative radiative force, the cumulative impact of methane divided by the cumulative impact of a reference substance, which is CO2. Because CO2, the global warming is expressed typically in CO2 equivalent. So CO2 is the carbon dioxide is the reference. So you see that is the ratio between these two areas over a specific time horizon. In this case, 500 years for example here. Now, what is the point? That is the point that if this is how it works, then a dynamic account will be more accurate than a static one. The two options that I was showing before, although still with some limitations. For example, this pulse profile is theoretical, but in reality, it might be a bit different. Applies only to well-mixed greenhouse gases in the atmosphere. So scientifically, there are some limitations. The time horizon still is arbitrary, even if you use a dynamic approach rather than a static. And CO2 has infinite residence time. So even time horizon will, in any case, will cut your part of your impacts out. Then when it comes to the discounting of long-term emission with respect to short-term, which is the issues that I was saying before about the weight, that if you emit earlier, you get more impact. How to show that? So if you have an emission at time 0, of methane, the profile will be like that. But if you emit at time 50, then the profile will be this one. Now, the part in red here is how much of impact you consider up to the time horizon, in this case, 20 years. So you see that in the second case, you have less of this area, which is included in the calculation. That is why you get a lower characterization factor and then lower impact per the same amount of gas emitted. Yeah. So what are the recommendations from our project on how to deal with these two issues, the modeling of biogenic carbon and the dynamic accounting of the timing of the impacts? Well, first of all, you can find everything in this document linked here. I have also a QR code later that you can use to access this directly. So what we discussed in the project, what we think is a sound approach to do that is that, first of all, we recommend to have, when you do your LCA of a bio-based product, that you have the system boundaries cradle to grave. So you include the entire life cycle, not only cradle to gate. Please note, I'm talking about full LCAs. I'm not talking about making data sets for databases, which is a different story. These are always truncated or very often. So I'm talking about making a full LCA for a product. It should be cradle to grave because it's a life, otherwise it's not a life cycle in a way, but only half a life cycle. In the inventory phase, we document to report separately all biogenic and non-biogenic carbon flows. In this way, you can apply different impact assessment methods. Always do it, you can. For a climate impact scores, we recommend to compute at least 2 indicators, a short-term and a long-term effect. This translated in English means using different time horizons for the global warming impacts. Then we recommend to use the +1 minus -1 +1 approach so that all the biogenic carbon is accounted as well. And this we do because in connection with this previous recommendation that we have a cradle to grave study. So we minimize the risk of having misleading results because of a truncated product system. And then you can present the results, whether biogenic or fossil or together, but we recommend to at least include a total indicator that includes the contribution of both biogenic and non-biogenic flows. And at least include the time effects provided with a tiered approach. I'll come back later to that, because when it comes to doing the dynamic assessment, this is usually more data and resources intensive. So we have designed a sort of guide that, based on the time and resources that you have and the degree of complexity that you can afford, then you can make a more and more accurate model or complex model in a way. We also have designed a sort of flow chart here, decision tree. And if we start with the use and end of life phase, which is usually what, if you remember, we started here from the cradle to grave part recommendation. So here again, we start from the same issue about system boundaries. If the end of life and use phase are known, are not known, then and cannot be either estimated or modeled, then you are forced to do a cradle to gate model, even though we don't recommend it. In that case, we recommend to make clear what is the share of the since we're using a +1 -1, make clear what is the share of biogenic carbon uptake and biogenic carbon impact in the score. And then, even though you don't know anything about your end of life, try to make 2 contrasted end of life scenarios so that you can close the carbon cycle, the accounting of the carbon cycles. If you have information about cradle to grave modeling, at least from primary data or from my estimations or from assumptions, then the next key thing is whether you want to claim that carbon is stored during the life cycle. So if this is the case, then you can include the time effects using the dynamic approach as in 3 different complexity levels. If not, or if this is not the case, and when is it not the case of carbon storage, then okay, we had a lot of discussion here in the project because in some standards, in some guidelines, you will get a sort of arbitrary time horizon. So if it is more, if you store the carbon for more than 100 years, then it is permanent. If it is less, then it's not stored, and so on and so on. But we couldn't we don't think it is reasonable to have a just arbitrary time horizon in that way. So we discussed that if your unit, if the carbon is stored for a time longer than your unit of analysis, which is the time that you use to collect the data, then you should not. You need to include the time effects. Otherwise, it is not. So if you study a product which has a life cycle 1 year and all the data are collected for that time frame, and then carbon uptake and release happen in the same time as the data, then focusing too much on the dynamic effects might be like overkill, and you can get the same conclusions with a static approach. But the rest of recommendations apply for that case. There is more detailed explanation of that in the document that that you can find online, that I showed you later where it is. This is explanation, no, just a very quick kind of flash of our different tires for using the dynamic approach. And you can see that basically from left to right, the model increases in complexity. So for example, in the time step for the dynamic LCA characterization factors, when in a base level, you need to know when the different, for example, stages happen. So the time for the biomass sourcing, production, use, and end of life. So you need only 4 data points. And when you apply this to a very detailed level, then you need a specific time profile for your emissions for all your inventory flows, all your inventory in a way where you have carbon uptake and release. I won't go more in detail in that, but just to give you an idea that this is designed to see the trade-offs between simple model that gives you some conclusions but less accurate, and more complex model that takes more time, more resources, but gives more accurate results. Where do you find all these tools that we have provided, and these guidelines that we have provided for as part of a project? So they are part of our deliverable 1.2 description of scientific methods. This is a big deliverable, and there's a lot of documents. They follow the ISO phases. So we have documents for inventory, for goal and scope, for self-impact assessment, interpretation. And in this presentation, I'm only focusing on the ones about life cycle impact assessment. Specifically, we have methods and characterization factors for dynamic assessment of climate change and assessment of biodiversity impacts. In this presentation, I've been only focusing on the climate ones. The deliverable includes a series of very different documents. There are some guidelines, there are tutorials, there are routines, algorithms, templates, there are data sets, there are models, calculators, and then there is code for those who are into coding. And everything is available open access. Where do you find everything? So you can go to the main page. This is a Zenodo community called Aligned Community, where all the repositories are grouped in a way. And then once you find now one of the repositories, then you can access it. And then there is a description of everything which is included there. And there are different methods. Then corresponding to that, when all of them described, of course, then corresponding to that, there are a list of files. So you find the file that you need and you can download it, of course. Please check the license, which is CC BY 4.0. And then you can also cite this document. In the specific case of a method for life cycle impact assessment, we have a repository for that. It includes a guide on the life cycle impact assessment for bio-based products, climate change and biodiversity. This is the guide that includes, for example, the recommendations that I just described in these presented in this few minutes ago. Then there are the tools for deriving dynamic characterization factors, a tutorial for including the time dependencies with the tiered approach, data sets with biodiversity characterization factors, and tutorial on how to import that Python. Other things, here is an example of the dynamic carbon footprint calculator characterization factor calculator tool. So you can, there is a README, with a spreadsheet, so Excel, and there is basically you can calculate different global warming potential indicators, different time horizons, and dynamically based on a so that you can use in when you have a sort of time specific emission profile for your greenhouse gases. That was it. I don't know how I am with the time, but that was it from my side for this presentation, and I'm happy to answer any question.
Thank you, Massimo. I think we are very much on time. So, and we have different questions also that even some participants started to respond to each other. So very engaged audience we have. If you would like to.
Can you select any of the questions for me, or should I just scroll through that? Oh, there are so many questions. So this one, when you say approach -1+1 takes into account only net flow and not sequestration, what do you mean? Yeah, thank you for the question. So if you account for all flows, you have both the uptake and the release at different times. So in this way, you don't have to have a separate flow about sequestration, because sequestration is only a matter of time. So either this is an uptake that is never released again, and then you have a minus, or it is an uptake that then is released afterwards, and then you have a minus and a plus, and they might balance or not depending on the time. So you don't need a specific flow about sequestration. That was the case in the 0-0 approach, because in the 0-0, biogenic never, you don't see it, you never see it. So if you have a situation where the carbon is stored indefinitely, for example, you have no way of, biogenic carbon is stored indefinitely, you have no way of seeing that. So that is why you have this extra flow about sequestration. So I hope this answered the question. There is a question here that was asked before about the cascade, so that the biogenic carbon and biomass can cascade across many different value chains. How are the open loop recycling strategies addressed in LCA, meaning that there is no grave? Yeah, I'm not sure what the question is exactly, but this is a open loop and closed loop recycling is a way, you can model this in different ways depending on the guideline and depending your approach. If you use a sort of allocation or if you use a substitution, you will have to do it in different ways, but it doesn't change the fact that in all these cases you will have to account for carbon anyway. So I think our recommendations are agnostic to the type of modeling approach that you use to model the open loop or closed loop. However, I would maybe be a bit careful if you are not if you account for biogenic flows, but then you don't express them in the impact phase. That is one thing. But if you don't account for biogenic flows because you know already that you want account them in the impact assessment phase and you just decide to exclude them, then you might have some issues in your LCA of mass balances that are not balanced. So I would recommend to keep, that's why we also recommend in the project to account for everything so that you can get some real world mass balanced inventories at least. Then what happens afterwards when you do allocation is another story again. But for what concerns this presentation, I think the accounting try to count all these flows, even if you don't want to use the +1 -1 method, but still keep them in the inventory because maybe somebody else want to do that, or maybe, or first of all, it allows you to have a more representative accounting of your system. Yeah. There is a question here about the large companies that are requested to update their scope 1 greenhouse gas profiles is every 3 years. Well, it's not a question. Sorry, it's an answer.
Yeah, I think they replied to Milena. So Damien replied to a previous question.
Okay, good. Damien is the contributor to this presentation, so I think he's qualified to answer. Thank you, Damien, for contributing to the discussion. Yeah, there was a comment here that we skipped before, right? From somebody here about the environmental footprint 3.1 method. If you use that method, your carbon footprint calculations will not include the biogenic CO2 and CO emissions. This is, as I just presented, is using the 0-0 approach, so you don't see the contribution of the biogenic emissions and uptake. This could lead to underestimating the total greenhouse gas emission associated with the production of bio-based products if a full carbon cycle is not considered. Well, it will underestimate in any way, let's say, even if a full carbon cycle is considered, because even if it is considered, you don't see the uptake, you don't see the release. But yeah, I confirm. So this is exactly the effect. If you use this approach, you will not see any contribution from the biogenic emissions. So they are so also your interpretation of results should take this into account. So that was correct, almost entirely. Let me see. Okay, here is a good one. Is the account of time considering the impact of a product process done now through the years, or is it considered how will the impact be in case it will be done, for example, in 20 years? No, the time accounting is independent from your choices. So you could have a time accounting in both cases. So you could have a scenario where your product is produced now and a scenario where your product is produced in 20 years, and then the emissions will have happen at different times depending on the product. I don't know if there is a use stage and you have carbon emission use stage. Let's imagine then this use stage will happen in 20 years from now. Then this, if you use a dynamic accounting, then the impact will be different if this use stage would have been happening right now. So in particular, we will have a slightly lower impact because, as I said, emissions that happen later are kind of discounted or given less weight because of the way the indicator is constructed. But this is supposed to reflect actually the physical reality, you know, that emissions are postponed. So the impact is not happening right now, it's happening in 20 years. This is different than having it now. So I hope this answers your question. So it's I guess the answer is yes, is the account considering the lifetime. If you have a lifetime that is in 20 years, you can specify that. Are you in contact with contributing to life cycle initiative biogenic carbon project? Yes, some people from our project are in contact with those. Thank you. What else? I mean, there is a question here on binders, but honestly, I don't know how to answer that because I'm not an expert in binders. Sorry, so we didn't answer that in the previous sessions. This is very specific to a certain type of products. So I'm not qualified to answer that. Unless I can only say, use our alignment recommendations, even if you, and I mean, when you do your LCA of binders, because we think they are good ones. So I hope that answered your question. I don't know. I think I went through most of the questions, so we are a bit ahead of schedule, maybe, but maybe we can wait a second and invite the people to post more questions. I mean, the ones that are still here, I think they have been covered already in various answers. And some are a bit unclear, sorry. What do you say, Rocio?
And there's nothing on the chat, so I think we answered most of the questions, and maybe we can move on to the closing remarks if everyone agrees. And just a friendly reminder, this video is being recorded and we will send it to you by email next week with all the presentations, with all the slides, and also the contact information. So if you have a new question, maybe these days, maybe the speakers can answer you.
Okay, then I will stop sharing.
Yeah.
And thank you all for the questions, by the way. It was really good to get them.
Yes, from my side, I would also like to express my gratitude to everyone to make this event possible. I mean, I think we reached almost 120 participants. So a big thank you to the speakers, to Leo from Arditech, Massimo from Aalborg University, Aitor, because I think you put a lot of time and effort in preparing and delivering this presentation, also addressing all the questions. And also would like to extend my gratitude and my appreciation to Rocio from Sustainable Innovation. I'm very glad to have collaborated with you in making this event. And of course, I want to thank all the participants. We received more than 300 responses in our forum. Today, as I said, we had more than 120 attendees. I saw all the participants very active. They made such thoughtful questions, and I think it really enriched our discussion. So I hope that was valuable experience for all of the participants. You gained valuable knowledge that you can apply directly to your work. And yeah, I think you will also receive a post-training feedback form after this event, so you can fill it out. It will be very helpful for us for improving events and also to assess how was this activity and to even organize other future events. And as Rocio said, you will have the recording and all the slides. So once again, thank you very much.